Okay, we have introduced the equivalency notation that here we're going to consider the cardinality of the set of real numbers. So unlike the set of integers or the set of rational numbers, which are called countable, and their cardinal number is denoted by LF0. And here we're going to consider the cardinality of the set of real numbers, which absolutely is much more. They have much larger cardinality than the set of integers and rational numbers. So what is the cardinality for R, or for the set of real numbers? The notation is the LF1. So we said that R is to have the cardinality N1 or LF1, and this cardinality is also called the cardinality of the continuum. And we can also use the C to denote it, or the A1, and informally it is also the 2 to the LF0. Okay, so LF0 is the cardinality for natural numbers or the countable sets. Okay, so we should see this intuitive reason for this. All right, so now let's recall that in analysis you learned that we can construct a ordered field as Q. So we say you start with the natural numbers, right, which is 1, 2, 3, 4. Just simply enumerate the items. This is the simplest. This is the first thing that we can construct. It's the most intuitive one, and from there we can construct the set of integers. So we include 0 and all the negative integers, and we'll get the set of integers. And then from there we'll get Q. So we introduce the notation of multiplication and the inverse of the multiplication, which is, which gives us all the fractions or ratios of integers. So get the Q. The Q is a ordered field, but the Q is not complete in the sense that we can generate a sequence of rational numbers, and they converge, but the limit of this rational numbers is not a rational number anymore. Okay, and then when we complete it, we got the set of real numbers. Okay, so this is the one way this is the original way that we define the set of real numbers. And to intuitively understand why this R has a cardinality equal to 2 to the RF0, let's recall that, first recall that if I have this kind of sequences, so I define F to be the set of binary sequences. What we mean by that is I have a sequence, I call it x1, x2, okay, infinite sequence. And for each of this x1, x2, it is either 0 or 1. All right. Okay, so this is just a collection of binary sequence. Binary means that each component is either 0 and 1, or 1. Okay, I will claim that this set is uncountable. Okay, the reason, so apparently it is an infinite set, right? It has infinitely many elements. I'm going to claim that it's uncountable. The reason is, let me see, claim F is uncountable. Okay, the reason is, if not, then that means if not, then F is countable. Then we can enumerate. So let's say I can just list the elements of F as this. So I have the first sequence or first element, I call it x1, and it's just x the first component of the sequence, second component of the sequence, third component of the sequence, so on and so forth, right? And then the second element in the set F is a sequence, is again a binary sequence. The first component, it's the second component, third component, so on and so forth. Okay, so that's the infinite sequence. I can just keep doing that. And now, since I enumerate all of them, so these are all the elements in F. Okay, suppose this is the case, then I'm going to give a new sequence, which is also binary. Let's call this sequence Y. Okay, and this sequence has this Y1, Y2, Y3, so on and so forth. So how we get this Y1, Y2, Y3? So my Y1 will be the value that is different from x11. So that means if x11 here is equal to 1, then I set my y1 to 0. If x11 is 0, then I set y1 to 1. Okay, and similarly, I will check this value. If it's 1, then I set this y2 to 0. If this is 0, then I set y2 to 1, just to be different from the 1. So similarly, this will be different from x33, so on and so forth. Okay, so I get this sequence of a y, and apparently this y is also a binary sequence because each component or each iterate is either 0 or 1. So y actually belongs to F. Okay? As you can see, y will belong to F because it's also a binary sequence. But y is different from any of those, right? Because everyone, so it is different from x1 since these two are different. These two are different. So the y is different from x1, is also different from x2, is different from every one of them. So here is a contradiction. The y, we show that the y belongs to this set F, but it's different from any of the elements of F that we enumerated here or listed here. So that's the contradiction, and that is why that it belongs to F, but the y is different from any of those. So this two gives us a contradiction, and that means this F cannot be countable. Okay, next let's see for any real number x in this interval, half open, half closed interval. So x is strictly greater than 0, but it's less than or equal to 1. So for any of this real number x, I claim that they can be written as this infinite sum, okay, or this series. It's an over 2n, 2 to the n, where an is either 0 or 1. So the reason is, recall that I have a real number on the interval from 0 to 1. Okay, suppose the x is here. So this is my x, and apparently to get this x, I first need 1/2. So this is the 1/2, and then I will check if I add 1/4, does it reach x? If it surpasses x, then I'll set a. So here, say this is a 1 over 2 plus a 2 over 4 plus a 3 over 8, so on and so forth. So as you can see, if by adding 1/4 it will surpass the x, then I will set a2 to 0, and then I will check 1 over 8 and see if it is 0 or not. Okay, so once it's what determined is 0 or 1, then we move on to the next element or next term in the series. And then by doing this, we can imagine that this will add up to this x, right? Because the difference between, so you gradually add up new components, and the gap or the progress you make is getting smaller and smaller, and eventually they will convert to x. So this is a sequence of rational numbers, and they will converge to the x. Okay, so every real number x can be written in this way. So you may ask, what if, say, what if I have this finite many of those ANs as non-zeros, and starting from AN, you become all zeros. I have, say, 1/2 plus, say, 0 over 4 plus 1 over 8. Then all the others are zeros. So in this case, I will change this term. I will change this again back to 0 over 8 by put 1s on all the others. I put this as 0 and put 1s on all the others, and you know the sum of this tail will be equal to 1 over 8. So I didn't really change anything. So here is the rule I'm going to make. Every sequence I have here will have infinite many 1s. If I only have finite many 1s, what I can do is replace the last one by 0 and all the later ones to be 1. All the later ones to be 1. So in this case, even if I have only finite many ANs as 1s, I can convert it to a sequence of ANs that has infinite many 1s. Okay, so by doing this, as I showed earlier, all the real numbers, not including rational numbers and irrational numbers in this interval, we can use this notation to represent it. And now you can see, first of all, if this, I can make an equivalency between this x and the sequence ANs. So the x can be equivalent to the sequence A0, A1, A2, so on and so forth. So this is an infinite binary sequence, as we showed earlier, and this is the infinite set. This is the uncountable set of those, right? There are uncountably many of those. And although we remove the sum of them, so we consider the sum. We do not consider those with finite many 1s, but you can imagine there's only finite many. There are only countably many of them. So let me repeat what I just said. I make a kind of one-to-one correspondence between x and this infinite binary sequence. Okay, I make a one-to-one correspondence between these two, but at the same time, remember that I do eliminate some of those binary sequence. For example, 1, 0, 1, and all the others are 0. This is also a binary sequence, but I converted this into 1, 0, 0, 1. All these others are 1s. Okay, so I converted into this. So in this case, I actually deleted this from the set of binary sequence. But this kind of sequence corresponds to rational numbers, and those rational numbers together only form a countable set. And this kind of binary sequence itself is uncountable set. So that's why even if I remove some of them, I still have a uncountable set left. So I correspond each x to one of this sequence, and I know that this x is actually uncountable because they are corresponding to a uncountable set of binary sequences. Okay, so this is to realize that this is actually this interval is actually uncountable, and also because we said the set of binary sequences is just having this kind of form where each one of them is either 0 or 1. So remember that if I have three, I would say three, say I have three drawers. And for each one, I have either a black ball or white ball to put in. So I can choose to put in either the white ball or the black ball into this first drawer, and it just put one of them. Cannot put both of them. So then I have two choices, and then for the second drawer, I can also do the same thing. I'll have total of 4 choices, right? So for each one of them, I have 2 choices, this also have two choices, but I have countably many of them. So if I have just three choices of them, then it's 2 to the 3. But I have now countably many of them, so it's 2 to the n0. Okay, that's the reason why I said here that this is actually the n1, which is the cardinality of the set of real numbers, is actually equivalent to 2 to the n0, r left 0. So r left 1 is just the r left 0, 2 to the r left 0. Now let's look at an example. So first, you look at if you have a set an that has cardinality r left 1, so it has the same cardinality of the set of real numbers, and if this is true for every n, then the union of them is also r left 1. Okay, the reason is what we're claiming here is for every, if I have a countably many sets where each one of them has a cardinality r left 1, then the union of them is still a set and has cardinality equal to r left 1. So to show this, it's easy to show that I can, because it's r left 1, so I can make an equivalency between this set and the r, right? And then similarly, I can just make it equivalent to the set 0, 1, because this interval also has the same cardinality r left 1. And this is the same as, say, n and n plus 1, right? I just shifted them to the new position. And now you can see when I take the union of an, what I will get is just the union of n and n plus 1, and that is just n to positive infinity. And you know this is a subset of R, and it is also uncountable, so that means it is it has cardinality r left 1. Okay, so that's why the union of this can be shown to have cardinality r left 1, and that is the claim we're making here. So that's the first one. A second example is, so you look at the Rn. Okay, so the n-dimensional Euclidean space has the same cardinality of the set of real numbers, and they're all equal to r left 1. Okay, to show this, it's similar to the one above. You treat each r as an, and then the union of them is equivalent to the Rn, and which has the same cardinality r left 1. Okay, just equivalent each r with an, and then Rn is equivalent to the union of k from 1 to n ak. Okay, and each one of them has this r left 1 as the cardinality. So that's why this one will have the same cardinality r left 1. Okay, so the last thing we're going to show in this section is a question on the cap of cardinality or cardinal number. So we think that we can we saw the cardinality, finite cardinality, which is n, right? So if it only has finite many, a set only has finite many elements, say n elements, then the cardinality is n. If it's countable, then the cardinality is LF0. And then we also see cardinality N1, which is can interpret it as 2 to the LF0. So the question is, if we will stop here, or if there are even larger set. Okay, and the theorem I'm going to show next is that we can never really find a maximum cardinality, because no matter what cardinality number you have for a set, we can find a set with larger cardinality. Okay, so here is a theorem. It says that suppose the a set is non-empty, then it cannot be equivalent to its power set. So what this power set means is defined as all the possible subsets of the set A. So it's all the subsets of A. Okay, sometimes this is also written as the P of A, the power set of A. Okay, so how to show this? Let's do the proof. So if not, then there exists a one-to-one correspondence called F. It's a mapping from A to its power set. Okay, now remember that A is a set of elements, and the 2 to the A, the power set, contains all the possible subsets of A. So in this set, this set is just a bunch of, it's just a collection of subsets of A. Okay, so for every element, say in here, it will be mapped to this, but this is a subset of A. Okay, so this is what I'm trying to say here. Now, let's consider this special set of A. So this set is a collection of elements in A, such that, remember that when map this X using F, I will get a subset of A. So this is a subset of A. And then since it's a subset of A, I can say if X is in this subset or not, right? So I will just collect all those X such that the X is not inside F of X. Okay, so this is a collection of the elements in A. So all the elements who does not belong to F of X will be put in this set B. So this B is a subset of A, as you can see, right? And since we have a one-to-one correspondence between A and the power set of A, and the B is a subset of A, so that means B belongs to, it's an element in the power set of A. Okay, and since F is a one-to-one correspondence, that means there exists a Y in A such that the F of Y equals to B, right? This is because F is a one-to-one correspondence. And now we'll have some, we'll have contradiction. Because this is the case, so I can consider the case 1. If Y belongs to B, what happens is if Y belongs to B, that means Y belongs to F of Y. And because of this, this is a contradiction to the fact that Y is in A. It's a contradiction to the fact that the Y is in B. Right? The reason is B only contains the elements who are not belonging to the F of itself. But now y belongs to f of y, that means y cannot belong to b, and that is a contradiction. Okay, so that's the first case. The second case is y does not belong to b. Okay, so y is either in b or not in b. If y is not in b, then that means y is not in f of y. Okay, because f of y is just b itself. And y is not in f of y, and it is supposed to be one element in b. And that is again a contradiction, because at the beginning we said that in this case we consider y not in b. So that is another contradiction. So in either way it is a contradiction. So that means this f cannot exist. We cannot really find a one-to-one correspondence between a and a complement, the power set of a. So that means this cannot be true. Okay, so we cannot find a one-to-one correspondence between a and 2 to the a, but at the same time 2 to the a definitely has a larger cardinality of a, because this we can always extract every element of a and form it as a set, and it will belong to this. So definitely this one has a larger cardinality than this one, and we said that we proved that there is no one-to-one correspondence. That means this one has a larger cardinality than this one. Okay, so as you can see, what the theorem says here is that as long as the A is non-empty, the power set of A will have a larger cardinality. So that means I can consider the power set of this set of real numbers. I will get a set with larger cardinality, and then with that cardinality, I can consider the power set of that, and I will have an even larger cardinality. So we never stop. We can never get a maximum cardinality. Okay, so that's the proof that theorem we're going to show here. So now what we showed, as we just proved, there's no way to really stop, right? There's always a larger and larger set. But now between these two, we definitely cannot see anything in between, right? You can see it in extremely large, but either it's finite or it's infinite. As long as it's infinite, it will be at least countable. And the question is, what is between this and this? Is there any set that has a cardinality larger than RF0, but is smaller than RF1? This is still an unsolved problem in mathematics. So at this point, up to date, there is no answer for that. So people are still looking for answer to see if there are anything in between. Okay, so it's just something that you need. You know that there's still unsolved issues in the theory of analysis. Okay, next we review the concept of topology of matrix spaces. Okay, we're going to review some of the most important concepts, and also give you some new concepts that will be used in this class. Okay, the first definition is Euclidean space and norms. So we know that this Rn is the set of vectors, n-dimensional vectors, where each one of them is a real number. Okay, the norm of a vector is denoted by the norm of the vector x is defined as the square root of the summed squares. Okay, so it will be a non-negative number. Is called the norm. Okay, so this is the basic norm that we use. You can define other types of norms, one norm, two norm, three norm, all those things, but we're focusing on the two norm in this class. Okay, so this is the n-dimensional Euclidean space. and this is the norm of x. Okay, and then we can easily verify the following properties of norms. So first of all, the norm, as we said, has to be non-negative, and also the norm is 0 if and only if the vector x itself is 0. Okay, it's 0 vector. If you multiply the norm by any real number, this will become the absolute value of the number a and the norm of x. So remember that these two have different meanings. X is a vector, a is just a scalar. So this is true for any real number. Okay, so if you like, you can put this as the on top to denote this vector. So for this case, we are not going to distinguish that. So the norm of x plus y is less than the norm of x plus the norm of y. Okay, this is called triangle inequality of norms, and it can be proved since our x is defined in this way. So they can be proved. This can be proved using the Cauchy-Schwarz inequality, which is very useful, very commonly used in mathematics. Let me recall you what this one is. So suppose I have, it's called Cauchy-Schwarz inequality. So suppose I have two vectors x and y. Then the x1, y1 all the way to x n, y n. This is like the inner product of the two vectors. It is less than equal to the norm of x times the norm of y. Okay. So how do we prove this? So to prove this, let's think about a function f defined as a function of a scalar lambda, and this function is defined as the norm of x plus lambda y. And according to our definition of norms, first of all, x plus lambda y is just a vector of x1 plus lambda y1 all the way to xn plus lambda yn. And the norm of this, according to our definition, is just x1 plus lambda y1. Let's be defined as the square of this. It will be x1 plus lambda y1 square plus x2 plus lambda y2 squared all the way to last one, which is xn plus lambda yn squared. So if it's just a norm, then I need to take the whole thing, take the square root of the whole thing. But then since I square it, so I'll just have this. And then you can expand the terms. I have x1 squared plus x2 squared all the way to xn squared. That's the first term I can get from each of these n terms. And then I will have the 2 times lambda x1 y1 plus x2 y2 all the way to xn yn. And then finally I have a lambda squared times y1 squared all the way to yn squared. Okay, and you can see that the first term is x norm squared. The second term is 2 times lambda times the inner product, which is x1 xi y. Let me just write it for short. Right, and then we have the lambda squared times the y squared. Okay, so on the one hand, you can see this f of lambda is a quadratic function of lambda, meaning that it is written as something times lambda squared, and something times lambda, and some constant. So this is on one side, it is a quadratic function. On the other hand, it is always greater than or equal to 0, right? Because this quantity, it is defined as a squared norm, which is always greater than or equal to 0. So what kind of quadratic functions are always greater than or equal to 0? It is, the quadratic function should be either this or this, which is touching the set of real number, the number line. It cannot be this, right? So in this case, we know that this is always greater than 0 for the lambda, which means, the criterion is that b squared, so you have so you have ax squared plus a lambda squared plus b lambda plus c greater than or equal to 0. That means b squared minus 4ac will be less than or equal to 0. Okay, so now this is like the a, this is like the 2 times this is like the b, this is like the c. Okay, so I can show that the b squared, which is this, minus 4ac, or it should be less than or equal to 4ac, or minus 4ac less than or equal to 0. 4ac is 4 times x squared y squared. Okay, so now you can see on the left hand side, if I take a square root on both sides, I'll have 2i from 1 to n xi yi, and on the right hand side I have 2 times x y, and then I cancel this 2. That is the Cauchy-Schwarz inequality. Okay, so the only chance that it can get this as equality, mean here, the only chance that it can get this as equality is that y is a multiple of x, or x is a multiple of y. It means that x is some scalar times y, or y is some scalar times x. This is the only chance that this is the equal. Okay, and when this is the equal, when x is a multiple of y, or y is a multiple of x, then you get this as equal. This is the only chance that you get equality of this. But in general, this is less than or equal to. Okay, so next definition of metric space. So let this X be a set, and the D is considered as a mapping from the Cartesian product of X with itself to the set of real numbers, actually non-negative real numbers, and it's called a metric if the following 3 conditions hold. The first condition is, D is a mapping in this way. That means for every x and y, it will take these 2 numbers or 2 elements and you will get a real number, right? So the dxy is greater than or equal to 0, and also dxy equal to 0 if and only if x is just the y itself. It's the same element as y. The second condition is that the dxy is equal to dyx for any x and y. The third one is dxy be less than or equal to dxz plus dz zy or dyz, doesn't matter because it's symmetric. Okay, so this holds for any x and y. This holds for any x, y, and z. Okay, so we call this D a metric if it satisfies all these three conditions. Okay, and in this case, we call this X D a metric space. So if we do have this D defined on X, then we call this a metric space. And sometimes if the D is clear from the context, we just call X as a metric space. For example, you can consider the D between two, let's say X is the Rn. D of X and Y is defined as the norm of X minus Y. X and Y are n-dimensional vectors. Then you can show that X and D is a metric space. It's a metric space. Okay, and the only thing you should check is that D satisfies those three conditions. And because of the property of norm, you can easily verify those three. So once you have a norm, you can use that to define this metric. Okay, so next we're going to give a sequence of definitions regarding the metric spaces. Okay, suppose that we're given a metric space X, and this metric is called D. So the first definition is called the diameter of a set. So E is a subset of X, and is defined as the supremum of the distance between 2 points in E. Okay, so as I said, E is a subset of X. Okay, this is called the diameter of E. Okay, if the diameter is finite, if this number is finite, then we call E bounded. Okay, so E is bounded if the diameter of E is finite. Second definition, open balls. So suppose X is a point in X or element in X, the delta is some positive number, then we define the ball of centered at X with the radius delta. So this Bx delta means a ball centered with X as a center and the delta as the radius is the collection of points in X such that the distance between the point in Y and X is less than delta, strictly less than delta. So this is called open ball. Okay, we call this Bx delta open ball. And similarly, we can define the closure of this, or otherwise whose distance from X is less than or equal to delta, and this is called a closed ball. Okay, and it would be easy to show this is just a closure, and we haven't introduced the closure later on, but now we just think that this is the collection of points whose distance is less than or equal to delta. Okay, we call X is an interior point if there exists a open ball. That basically means that there exists a radius such that Bx delta is completely inside interior point of E if there exists ball centered at X with some radius such that it is completely inside E. Okay, in this case we call the x a interior point of E. Okay, we see that E is open if every point of E is an interior point. Okay. So for every x in E, x is the interior point of E. Okay. So all the points of E are interior points. Then E is called open. And we call E is closed if the complement of E, which is just the x minus E, if this is open. So a set is closed if and only if its complement is open. Okay. But remember that a set doesn't have to be closed or even. It could be nothing, right? It could be non-closed but non-open as well. Okay. But what we have said here is that if the set is closed, then the complement will be open. If the set is open, the complement is closed. Okay. Next, we show that a sequence is said to converge. Let's say you have a sequence, which is a sequence of elements in X. We said it's called convergent, or it's said to converge to X. And we know this by limit of this for k going to infinity of xk is X. If for every element, for every epsilon greater than 0, there exists some integer that could be depending on the epsilon, such that for any little n greater than or equal to capital N, there is xn, the distance between xn or xk. So I should use k here. There is d of xk, x less than epsilon. Okay, so this is how we said the sequence is convergent to D. So in other words, that also means that the limit of the distance between xk and x for k going to infinity is just 0. Okay. A sequence is called Cauchy if, again, for every element greater than 0, there exists some n such that for all the k j greater than or equal to n, the distance between xk and xj is less than epsilon. Okay, you can also write this as the limit of kj going to infinity is x d of xk as j is equal to 0. So either way, but you need to understand that this Cauchy sequence actually means the this one here. Okay, so this is a generalization of the Cauchy sequence from the set of real numbers to the metric spaces. Okay, suppose I have a set E, which is infinite. I have an infinite subset of E, and we say that if there exists a sequence xk belong to E, so now you can see that E is infinite, so that's this is the case that we can actually extract a sequence from it, and I need those things to be distinct. So all those things are distinct means that x1 is different from any other elements or any other numbers in the sequence. So if there exists such a distinct sequence xk, such that xk convert to x, then x is called a limit point of E. Okay, so there are several remarks I want to make here. The first one is that this limit point is sometimes also called a cluster point or accumulation point. Okay, so they all mean the same thing. In general, most of the textbooks can use either one of them. The other remark I want to make here is that a limit point of a set does not have to be in the set. So say this sequence xk, every one of them is an element of E, but their limit x does not have to be in E. So it doesn't have to be a limit point doesn't have to be in the set itself. Okay. Let's say the E prime is denoted as the limit point of E, the set of limit points of E. So x is a limit point or accumulation point or cluster point of E. Okay, and the E prime denotes the collection of these limit points. Then the union of E and this E prime is called the closure of E. Okay, the E union of E and the set of limit points of E is called the closure of E. Okay, we can show that the closure of E, which is E bar, denoted by E bar here, is actually closed. And that's where we have the name closure. Okay, we'll show this soon later. And then we say that if A is a subset of B, and at the same time we take the closure of A, it is equal to B, then A is called a dense subset of B. Okay. So if A is a subset of B and the closure of A is just B itself, then we call a dense subset of B. Okay, we'll use this property or we'll use this concept a lot later. I will also give more definition or interpretation of this later. Okay, if X is in E, but X is not a limit point of E, then the X is called an isolated point of E. Okay, it's more like that you have this point x, and since it's not a limit point, that means you cannot really find a sequence of points that converge with x. That means x is living by itself, and you can draw a neighborhood or draw a ball centered at x that does not contain any point from E other than x itself. Okay. So this, let me say, this is equivalent to say that there exists a delta greater than 0 such that the ball centered at x with radius delta intersects with E only at this x point itself. Okay. Let's say I have a set of open sets, a collection of open sets. Okay, suppose I have this G alpha, where each alpha is the index. We call this an open cover of E if each one of those G alpha is open. And the union of this G alpha will cover E. Okay, so you can just think that you have this E here, and you have a bunch of G, each one of them is open set. So they all together will cover this G, will cover this E. So this is called an open cover. So you could have finite many of them. You could have uncountable many of them, or uncountable many of them, as long as each of them is open, and they all together covers E. So you can call it open cover. The last one we're going to give it here is that E is called compact if every open cover of E has at least one finite subcover. Okay, so first of all, what is a subcover? If you extract, you can use only you can use just a subset of this to cover the E. Then this is called a subcover. Okay, a finite subcover means that you can only use a finite many of them to cover the E. So the compactness is a very important and useful concept. It says that if it's compact means that if every open cover of E like this, doesn't matter how you originally set up this open cover, it could be finite many of them or could be infinite many of them. But no matter which open cover you have, you can always get a finite subcover of it to still cover this E. Okay, this is this definition of a compact set. Okay, the last one that we're going to say is that we're missing is that in the set of in the Euclidean space and the Euclidean space, we can define the boxes. For example, if it's in Rn, we can define this I to be, or any other notation, I to be A1, B1 cross A2, B2 cross so on and so forth to AN, BN. Okay, and this one is a subset or open interval in R. It's also open interval in R. Open interval in R. So this is analog to the boxes, like in R2 these are boxes, right? Open boxes means that the boundaries are not included. So this is called open box. Okay. So for Euclidean space, we can define this. We can actually get the we got these intervals to form an open box. So in 2D, it's just this. In 3D, that's just cubes. 4D, 5D, and higher, just a generalization of this. Okay, now we show several properties of the definition or concept we introduced. First one is that if x is the limit point of E, then if and only if for any ball centered at x, it contains some point other than x itself. Okay, the ball, for any radius, the ball centered at x with radius delta will intersect with E at some point. Okay, so this just means that if x is the limit point, then doesn't matter how you draw this ball with radius delta, there will be always some point from E in there. So it doesn't matter how small this ball is. So the proof. So on one side, this is easy, right? Because we, if it's a limit point, then there will be a sequence of distinct points from E that converge to X. So apparently, it doesn't matter how small you draw the ball, there will be some point from that sequence. So this is the trivial to show. And from the other direction, suppose we have, we know that for any delta, the ball X, Bx delta intersect with E with some intersect with E, then we can show that this X is a limit point. So to show that, say, let's set that 1 to 1. And then because of the property we have, we know there exists some point, x1, that belongs to Bx delta 1. So this is just the ball that we remove the center x. Since the other than the center, there's still some point, from E. So I know that there will be a x1 from this, and that will be the sequence, the first element in my sequence, and then I will add delta 2 to be, I will say, I want the next point to be closer to my x than this x1. So I'm going to make it as the minimum of delta 1 and the distance between x1 and x. Okay, so actually you know that this x1 will be anyway closer. The distance between x1 and x will be anyway less than delta 1. I'm just making this to be sure. So you can just use the dx1x. That will be fine as well. So you can use this as just dx1 and x is fine. But I'm going to make sure that it's really decreasing sufficiently fast. So I put 1/2 there. Then I know there will be x2. That is from the ball centered at x with radius delta 2 minus the x intersect with E. So you know that this x2, so let me draw the picture here. So originally I draw the ball centered at x with the radius 1. So the radius of this ball is 1. And I found some point. Say this is x1. And now I'm going to find the distance between x1 and x, and I cut it by half. and then I draw the second ball. This radius here is delta 2. And I know that from this ball, I will have another point, I call it x2 here. Okay, so this is how I got the x2, and apparently it's different from x1 because its distance to x is much smaller than that one the distance from x1 to x. So x2 must be different from x1. And just keep doing that. Suppose you already have xk, then I'm going to, so you already have the xk, then you're going to get the xk plus 1 by first setting delta k to 1/2 dxk x, and then find this xk plus 1 from the b of xk delta k minus x, there's x with e. We know that there's always some point in between in this intersection, so that's how we extract this. Okay, so then we obtain the sequence x1, x2, and this is the sequence, and their distance to x is shrinked by at least 1/2. So distance, as you can easily show, it is sk to x is less than or equal to 1/2 to the power k minus 1, okay, which goes to 0. So that's why we constructed a sequence which are distinct, and they converge to x. Okay, and this means the x is a limit point of E. The next theorem, I'm going to show that E is closed if and only if, in this way, if and only if the set of limit points of E is included in E. Okay, so this is actually an alternative definition for a closed set. If the set contains all its limit points, then it is closed. Okay, so to show this, suppose first that E is closed. Okay, so because E is closed, we know that suppose E is closed implies that E complement is open. Okay, it is open means that for any x in E complement, it is an interior point, right? This will be an interior point of E complement. So let's say I have x from x prime minus E. So this is in the E complement. Right? This whole thing here is in E complement, because the intersection of E complement and the E prime. So this is in E complement. So there exists say for any point here, then there exists a sequence of points in E such that xk converge to x. Okay, so now what we say is this is the set x, this is the E, and say this point here, x, is in the E prime minus E, which is here, and then it's in E complement. E prime minus E means that it's a limit point of E. At the same time, it doesn't belong to E, so it's in the E complement. Since it's in E complement, there exists, it is interior point. That means there exists a open ball such that it is, this open ball is completely inside the E complement. Okay, so now we have two things. On one side, there is a ball centered at X, open ball centered at X with the radius delta, such that this ball is completely in the E complement, means that it doesn't overlap with E. On the other hand, since X is a limit point of E, so there exists a sequence of points in E that converge to the X. So that is impossible, right? This is a contradiction, which contradicts X is an interior point of E complement. Okay, the interior point means that you can draw a ball, as I draw here, that it cannot include any point from E, but you have a sequence from E that converge to that. That's impossible. Okay. On the other hand, suppose E prime is a subset of E, then for any X in E complement, we know that X cannot be in the E prime, because E prime is a subset of E complement. The E is E prime is a subset of E, but the X is from E complement. So the E prime is inside here, and I have X from E complement. So I know that X cannot be a limit point of E, and if it's not a limit point of E, then that means there exists some delta such that the Bx delta intersect with E will be empty, or in other words, Bx delta is completely included in E complement. Okay, so this will be completely included in E complement. While if it's in E complement, that means this X is an interior point of E complement. Right? When we show this, for every point in E complement, there exists a ball centered at X with some radius delta, such that the ball is included in E complement, and that means X is the interior point of E complement. And its interior point of E complement means that an arc X is arbitrary. So any point of E complement is the interior point of E complement. That means E complement is open. And E complement is open means that E is closed. So we showed the other direction. If the E prime, or the set of limit points of E, is included in E, then E must be closed. Okay, the next one we want to show that the closure of a set is always closed. So say E is a set, the closure of E is defined as the union of E and the set of limit points of E, which is denoted by E prime. We want to show this is the closed set for any E. Okay, so to show this set is closed, we just need to show the complement of the set is open. So suppose there is any point from the complement of the set, So X is a point from the complement of closure of E. Then we know that X is in the complement of this, which means that X is not in E, it's not in E prime either. If it's not in prime, that means it's not a limit point. So that means there exists some delta greater than 0 such that the ball centered at X with its delta as a radius does not overlap with E. Okay, so what I mean is that there is a ball centered at X with the radius delta that does not contain any point from E. But at the same time, I want to show that this ball does not contain any point from E prime either. It does not contain any limit point of E. The reason is if it has some point from as a limit point of E, that means there's some Y in this ball that is also a limit point of E, then because it's limit point of E and this Y is in this open ball, that means I can draw this small ball. Y is in this open ball, so that means I can draw this small ball with a very tiny radius called R. And within this ball, there will be some point we call Z, and that Z is from E. Okay, so that means there will be some Z inside this small ball, which we denote by BYR, and that is BYR is small enough to be inside the larger ball BX delta. So we found some point Z that is in the BX delta. Now that is a contradiction to our setup here, where this BX delta does not overlap with E at all. So this is the contradiction. Okay, and by that we mean we show that the BX delta does not overlap with E prime either. Okay, so it does not overlap with E prime, it does not overlap with E, so it does not overlap with the union of them, which is the closure of E. So it does not overlap the closure of E, and that means this is in the complement of the closure of E. So now we show that for any X in the complement of E bar, there exists a ball such that it's completely inside E bar. That means X is an interior point. And since X is arbitrary, we know that every point is an interior point. Interior point. And since X is arbitrary, we know that the E bar complement is open. And therefore, E bar itself is closed.